Hi, in this video, we're going to take a look at spatial data analysis. All right, now for this video, we're focusing on composition data. Composition data is where for each observation I have, my variable measurements add up to a constant value, and all the measurements are non-negative, so zero or positive. So frequently we'll encounter this when we have like percentages. So if I have like soil samples, go and I pick up the soil sample and I look at what's in that sample, well, that's going to be, I can have that as a percentage. I can also represent my measurements as a fraction of the whole. In that situation, things would add up to 1. If there's percentages, things would add up to 100. And also we could do this in terms of parts per million. So, this is a very useful point of view. Now, in this video series, we're talking about geostatistics for composition data. And so now I'm going to ignore the composition aspect and focus only on the spatial aspect for this video. So everything we're going to talk about is modified from geostatistics for composition data with R, chapter 4. Here are the names of the authors. And University of Central Florida students can download the PDF of the textbook through Springer link through the library. Here is the GM Geostats GitHub page. Here is the professional website of one of the authors. And here are the CRAN pages for GM Geostats and the compositions package. All right, so let's get down to it. Okay, so when we're talking about spatial data analysis, we're first going to analyze my data that's not spatial at all, or I'm going to analyze my spatial data just only considering that. And then after I do both of those, I'm going to go and do my spatial full data analysis, considering both my measurements and my location. And so when I have composition data, first I'm going to analyze my composition data, ignoring the spatial aspect. That way I understand what's going on. I'm going to pretend I have no spatial components, and this will give me a better understanding of what's going on with my data. I'm going to analyze my spatial data, ignoring my composition measurements 100%. I'm just going to look at the points I have on the ground or in space or however it's set up, and just see what's going on, understand that, and then I'm going to look at the spatial composition data as a whole. All right, so why do we do it this way? I'm baby stepping into this. I want to understand it in a simpler manner and then get into things that are more complicated. This is similar to like when I have spatial temporal data. Imagine if I had spatial temporal data, then I would have a time aspect in addition to what's going on. And so then I'll be looking at time series without considering space. And I'll be analyzing that before I would get into the full-blown measurement aspect of it. All right, so when we do our analysis of the spatial data only, ignoring our composition measurements, we're going to do things like we're going to determine the types of spatial objects we have. Do I have points? Do I have a grid? A grid is just a special class of points, like a regular spaced out, regular interval points on the ground. Do I have lines like rivers or streets or something like that? Polygons, such as counties, states, countries, whatever it is. These are these cover like most spatial objects that we can encounter. Or maybe do I have a combination of them? And also, like, how is it stored in my machine so that I know that if I'm going to need to have to like convert to another format to be able to use packages that I want to use. Also, I'm going to just like look at the locations of my observations. I'm going to look at the bounding box. So I'm just going to look at the map, understand like how far east, west, north, south my data is, where is it located on the map, roughly speaking, just get to understand, what's going on. And, I'll check out the features of the spatial objects. The spatial object itself, does it have a data frame? Like in the spatial object, is the data frame, separated and is two separate objects? And then I also like want to consider the quality of my spatial data. Do I have missing values? Do I have observations in my data set that I don't have a location for? Do I have locations without observations? and get an idea of how am I going to handle this. Now, something that is going to come up when you do spatial statistics is that we're going to find that sometimes, like let's say that I've got information at county level, but I need it at the state level. Well, in that situation, I'm going to have to aggregate all of those counties to get a common understanding of the entire state. All right, so I'm going to aggregate multiple points together to get the state. So if my project is I'm entering the state, but I have counties, well, I'm going to do what I got to do. Also, another thing that can happen, it could go in reverse. Let's say that I've got county data across the country, but then I'm missing the counties for a particular state, but I have the entire state itself. Well, depending on my project, I might just have to say each county is connected to its state value, which is not favorable. That's not what we want. That's definitely not how we would want to do it. But if I'm missing a county, that might be the best way to go. Or maybe I could use other techniques, such as using like neighboring known regions. There's a lot of situations, a lot of judgment calls in data science that we have to make, grade decisions. And I feel like spatial statistics, it's even more pronounced because of all the things that have to go right to get good data. So a major tool for spatial map for us are spatial maps and plots of variables of interest against the coordinate directions, usually longitude and latitude. So longitude and latitude, longitude goes east and west, latitude goes north and south. How I remember it is that with X and Y, it's in the wrong alphabetical order. I just keep it in my head. It's wrong alphabetical order. So longitude is X, latitude is Y. Now, this works as long as we're staying away from the North Pole and the South Pole, which usually isn't a big issue. If we are close to the poles, then we need to, like the whole X and Y aspect, we need to change the polar or something like that. All right, so let's go ahead and start, run some examples. So here I'm going to load the Darling data set for the GM Geostats package. This is the package for the textbook. And the authors of the textbook made the choice to focus on a subcomposition of these 5 for these examples. All right. Now, something that they also do is that they say, all right, well, in my composition, I have iron, aluminum 2, oxygen 3, silicone, oxygen 2, Mn, and P. All right, and then whatever's not adding up to 100, that's every other thing I could possibly have in the ground. Okay, and so these are soil samples. And so what they choose to do is that they're going to say, well, everything else is just my residual. So I'm going to take the value that I know my data needs to add up to for each observation, and I'm going to subtract what I have of these variables. All right, so 1 minus all of these values is the residual column. The textbook calls it R. I like to call it composition residual. I like to be very precise in my naming. Okay, so now let's look at maps and plots. So first type of map we're going to look at is data posting. A data posting map is an image of a variable of interest where the coordinates of the data is generated with a location marker, either color coded or sized proportionally. And the magnitude of the variable observation that is of interest for that one map, it determines either the color or the size or possibly both. All right, and data posting maps allow the joint visualization of the composition from a spatial perspective. So I can see my variable of interest from a spatial point of view very, very easily. This is absolutely the most fundamental spatial statistics map you could possibly have. All right, there's also choropleth maps where we color regions such as counties, states, countries by a variable. Okay, so let's go through this. Now, we're going to specify that the coordinates of our data set are easting and northing. All right, so, normally we put longitude as east and west, and latitude as north and south. And so I put it in exactly that order. Here is my data set that I have. So only those variables of interest are being considered. Here are the locations, the coordinates. Here are the range that we have for the plot character size. And then I'm going to put a 3x2 for this. Now, the textbook did a 6x1. 6x1 looked very squished on in the R Markdown file. It did not preserve the aspect ratio. And so I went ahead and changed it to 3x2. All right, and so here we can see, that we have each of these going on. And so when you look at this initially, I recommend that you try to understand the extremes first. That's usually the easiest. That's true in data science across the board. Understand the extremes first, because that's usually the easiest, and then try to like work towards the middle to understand the more nuance. And so I look through the red. So for iron, I see red here and here. All right. And I also see blue in like that southern region. I also see a blue here. When I get over to AL203, I see that, well, where I had more iron, overall, I'm going to have less AL203 because, remember, I've got proportions going on. Overall, we're going to have negative correlation between our composition variables. Why is that? Well, think about if I only had two. If one goes up, then the other one has to go down because they add up to 1 or 100 or 1,000,000. So to maintain that constant value, if one goes up, the other has to go down. If one goes down, the other has to go up when I'm dealing with compositions. Okay, so overall, I would expect to see if it's high over here, it's going to be on average low at all other variables. If it's low over here, on average, it's going to be high on the other ones. All right, so I see the blue going on here. I see the red in the south, picking up that easily. Now, for SiO2, I see that I've got the south going on here, and I see a bunch of red in this region going on. I see the blue in the north band here. Now Mn, I see more of a east-west aspect. I see high values in the west and lower values in the east. For P, I see a big clump here. I see a large section here, and then this is a little bit less pronounced, but I see like a kind of a light aspect through here, and then the residuals. We just kind of have like what's left over, which is exactly what it is, and we see like blue in this region here. So low residuals. That means when I see small residuals, that means that the other variables accounted for the vast majority of what's going on. The measured values, the ones of interest, are present proportionately more there. When I see red, that means I had low, like other values that aren't of interest in the measurement are larger in the red regions. All right, if a spatial map with markers sized proportionally to the magnitude of the values is desired, a variable CX range needs to be adjusted to allow for different symbol sizes. I don't like this, by the way. All right, I like keeping the points constant and using color to represent. I don't like this changing of size business. Because this can exacerbate over plotting aspects. And so like not only is like high values important, but also low values are important in our plot. If I start making some big, they're going to get slapped on top of each other. So if I have 2 points, let's say 2 points like this, and this one here I make big, then it can shroud the other one. It can get plotted on top of it depending on the order in which we do our plotting, and changing the size can make this worse. Now there are advantages if I have like sparse data. If it's spread out, I like using this a lot more, but in the situation we have here with this data set, I don't like it. I wouldn't use it. So I'm going to use the technique in a moment And you'll notice the difference in the northeast section of P. So if I look here, notice that it's pretty intense. But then, I have things kind of like drop off as we move southward from there. If I scroll down, now here I'm changing the size. Look how big the dots that are red here are. They're pretty massive. And so this makes that intense region look much bigger than it really is on the map. So, you incorrectly get the impression that the areas of high P observations are farther north than the actual data collected goes and farther south than would be correct. And so I don't like increasing size for plots, but there's an advantage. If I had space between my points, like let's say I had a grid, I would definitely consider using it. But for this particular data set where you have overplotting, I don't like it. All right, so it's clear from the spatial patterns that iron generally have higher values in the north. SiO2 has higher values in the south and a region of high value in that central part of the southeast. There is a low-level Mn region in the center of the east bench of Windarling, and like this part here. All right, so one could think of this part as potentially high-quality iron ore with beneficial Me-Mn ratios. However, the SiO2 values of this region are very high, suggesting there's a dilution going on in the bulk of the chemistry. So the FeMn ratios are being diluted out by SiO2, irrespective of the ratio to iron. Again, highlighting the composition nature of this data. And so, the point that the authors are making here is that we need to consider all of them to be able to have a full analysis of our composition data. All right, let's go ahead and do additive log ratio transformation on our data and see if we can get some more information. On this data set, it doesn't really help us understand anything better, but it's a tool in our tool belt. So, this will be highly useful if, let's say, I had skewed data. If my composition data was highly skewed, then doing the log ratio transformations could definitely improve what's going on. All right, so to obtain a spatial map of additive log ratio transformed data, the input variables need to be recomputed in additive log ratio coordinates. And so I'm just going to go through and I'm going to do the additive log ratio transformation on my composition data. So what we're going to do here is that for every composition variable, I'm going to take the ratio of the variable with a reference level. So the way that it's set up by default in the composition package is that the last column is my reference level. And so that will always be in the denominator. And so what we're going to do, we're going to take the ratio of observed value over the residual, take the logarithm, and that is our additive log ratio. All right, so here I am just doing the transformation, and you notice that everything else is the same. And I'm sticking with what the textbook did. The textbook varied the plot size, the CEX range. And so now we pretty much reached the same conclusions on this particular map. You'll notice that composition residuals disappear because the ratio of composition residual with itself is always 1. The logarithm is always 0. So there's not really much to talk about because it's just a constant color across the entire map. So the R package just goes ahead and just skips it. In the case of the Windarling data, the difference between the spatial map of the raw compositions and the coordinates in additive log ratio transformation really doesn't produce a whole lot for us. This is due to the fact that we have a small interquartile range and the fact that the bench represents part of a high-grade iron ore deposit. All right, so now this is by far these dot plots with the coordinates of latitude and longitude are by far the most common way to handle spatial data analysis. But sometimes it can kind of be overwhelming and hard to see what the actual trends are. And so if there's like an east to west trend or a north to south trend, I would like to actually know that in a more specific, specialized manner. And we can use swath plots to do this. And so what I'm going to do, I'm going to pick a coordinate system or coordinate direction, and I'm just going to do a scatter plot of my target variable by the coordinates. And I'm going to try and understand it that way. Now, I don't have to limit this to latitude and longitude. I could actually go ahead and do like something like principal component analysis on my latitude and longitude to get a different representation in different directions. I can do anything that would be an isometry on the coordinates. I could also change up the my coordinates any way I want to. So let's say hypothetically my data goes from southwest to northeast, and because of maybe there's a valley, a river, however it's working out, maybe I want that coordinate system, instead of going north-south or east-west, I want to go parallel to the points overall. Well, you could use principal component analysis to do that, and I'll go do that. On this particular data set, it's like really not an issue. Like the first principal component is really close to the east-west direction. So there's really no reason to tinker with it, but this is a tool in our tool belt. All right, so a swath plot visualizes a variable of interest from our composition with respect to one coordinate direction. So the ones we were looking at previously, we had two coordinates going on. Frequently, a line plot of conditional averages or a spline are added to the swath plot to make it easier for us to spot trends. Also, we have the option of doing box plots by binning the coordinate variable values. In the GM Geostats package, the variables being visualized are the log ratios of the composition data. The result is usually a rough curve of the behavior of the values relative to the coordinate directions, and experimentation is required to obtain a plot that is interpretable. All right, so anytime I'm going to be showing plots to my stakeholders, I'm going to play around with things for a while to get things going, to get things as informative and easy to interpret. And then I'm going to present my results. All right, so here, this is default setting going east to west in the coordinates, and we can kind of see, the lines going on. I'm not seeing anything really strong. There are maybe a little bit here and there, but these lines look pretty flat. All right, now going with respect to north and south, I have, I'm not seeing a whole lot. The dots look pretty much like clouds, but maybe they did, maybe they didn't. I didn't know until I looked at this. Now, something to notice about this is that I have the same coordinates going throughout on my plots. If I go all the way across, I always have the same coordinate values vertically up and down. I have the same coordinate values, across. And so that might not be the best way. You'll notice I've got a lot of white space in these plots. Well, I can change this up, and I can work it out so that by changing the common scale to false, this will help me zoom in. All right, so you'll notice that I have a constant east to west coordinates going on here. If I put common scale equals false, you'll notice that things will change slightly in terms of that, and we'll zoom in. So what's going to do, it's going to take the largest value of the target variable for each row, the least value of the target variable for each row, and that determines the y coordinates. And it'll take as far east and west, or actually, yeah, for this one, east and west, for the column to zoom in. And so all of these have the same east to west coordinates, same east to west coordinates, east to west coordinates, east to west, in terms of the size of the bounding box. But we could potentially have differences across different columns. Now here, each row of observations can have different vertical scale, and this enables us to zoom in. You'll notice I have a lot less white space just kind of floating around in these plots. This helps me to zoom in and see things a little bit better. Like this little curve here, I could not see before. That might be interesting. Maybe there's something going on. But previously when I looked, that was, you know, completely hard to see. Like I didn't notice it at all. All this white space here disappears when I zoom in, changing the common scale. All right. And so here I have, you know, I do not have a common scale for the north-south points. So much easier to see what's going on. For the wind darling data, these diagrams show no real significant trends in the east-west directions, but some evidence for a difference in the north-south direction, especially for the ratio FE SiO2, MN SiO2, and MN Al2O3. So let's actually look at those. So Fe SiO2, we have, all right, so there's kind of a curvature here. We also go here, we see what's going on. Now, this is taking the reciprocal of the ratios before I take the logarithm. So there's a direct relationship between these two plots. Mn SiO2 is here, so we see a little bit of curvature going on these, and Mn Al2O3, so we have something going on here, and we have something going on here. All right, now let's talk about the spatial arrangement of outliers and subpopulations. Okay, so when we're conducting our spatial data analysis, you know, we'll have univariate outliers and subpopulations, just like in regular statistics. I'll have multivariate outliers and subpopulations, just like in regular statistics. Now that we're doing spatial, we'll have spatial outliers and subpopulations. So like, for example, Alaska and Hawaii for the United States, or maybe like Puerto Rico, American Samoa, Guam, the Mariana Islands. These are all geographically very far from the rest of the United States. And so, you know, like when I deal with these guys from a spatial point of view, these are outliers, and they're subpopulations, and they need to be treated as such. Well, we can have the same thing going on when I have a spatial variable outlier subpopulation. So, you know, here we're talking about not just a spatial outlier, not just a measurement outlier, but both at the same time. And so, you know, it might be that an outlier for Alaska is a reasonable point for the lower 48 states, but in Alaska, it's a very high value or a very low value. And in that situation, it's an outlier, and we have to deal with this. You know, there's a lot of layers to spatial statistic onions. Like, as you work through this, you just keep on taking the layers off as you work through. A final aspect that should be considered while exploring the data maps is the spatial arrangement of outliers and subpopulations. Our maps will help us visually spot these in ways that aren't apparent in the methods that we've used previously. The goal is here to evaluate the possibility that the spatial domain isn't well defined, and that samples at the boundary may need to be removed. This analysis is best done with dot maps colored by a categorical variable of interest, for example. All right, so let's go ahead and do a plot. All right, so if you do not load the compositions package, if you do not load the Geostats package into your system using the library function like I did, you're going to get different plots in the textbook. The plots I'm about to show you are not from the textbook. I avoid loading packages as much as possible. In R, there are plenty of times where two different packages will have functions of the same name, and you can be in the bad situation in your code that you think you're using this version of a function, but really you're using this one. And it's a really tough bug to break. And so you'll notice that's why I don't load packages if I can avoid it, or unless I'm going to be using them a lot, like ggplot, or I use a double colon notation if I can, as much as possible. So these plots are not from the textbook. The authors had the packages loaded, so they presented differently. But so this just helps us understand the pairs plot of the composition data. Now, here I'm going to do outlier classification. For this to run, you need to run, for this to run without loading the package, you need to absolutely have set sticky class option function called. And I don't know what the default is. I just set it to false and it looked good, so I just ran with it. All right, and now we're going to do composition outlier classification of the grade type. And now what the authors do in the textbook is they take the one categorical column in the data set and they take a look at the outliers versus that one categorical variable. We're dealing with soil samples, so the lithotype is going to be important to us. And so I've got OK, extreme, and outlier. This is, I believe this one is different than what the textbook gives. For output, future code will match. But we see we just have one basalt observation. We have schist observations that are all extreme or outliers. Okay, so this means that this is different than the rest of our data. And the bulk, I don't even know how to say these words. I'll just leave them as is. And so I can go through and I can plot these, pretty easy peasy lemon squeezy, and just get an idea of these. And this plot is also different than what the textbook gives because of not loading the package. All right, the map of lithotype shows that basalt and schist samples are located at the boundaries, mostly at the external boundaries. Even the three located in the inner part of the domain do not actually belong to unsampled regions inside the bench, which probably are not to be exploited. All right, so knowing subject matter about the sampling, these sampled points probably aren't even allowed to be used by our stakeholders, and so this is really just polluting our analysis. And so we probably want to get rid of these. Is correct, it's a legit observation, but it's throwing off the rest of the data of what's actually important to our stakeholders. So let's go ahead and remove these samples from the data set. Any categorical available can be analyzed in a similar manner as what we're doing now. For instance, with these results of an outlier exploratory analysis, so we can see that the map of outlier classification, so that there's two kinds of true outliers. There is a spatial cluster of them in the middle eastern part of the bench. Remember when I was hovering the cursor over that region when we looked? That's the area that he's referring to, they are referring to, and a dozen isolated outliers around the boundary. All right, these two types of outliers should be considered separately. So the inner cluster should be treated as a subdomain and analyzed separately, and the isolated outliers at the boundary could be removed from further analysis. All right, so let's go ahead and plot this. Now, these plots look different on my machine when I was in RStudio than they look here. I had different colors for some reason, don't know why, but I ran exactly the same code and these just visually look different. I had green. I had packages loaded as I was working through. So we're running the pairs map from GM Geostats. And here I've got my data. I've got lithotype and outlier classification. I've got my coordinate system set up. And I'm allowing some change in size of plots. And so here, so here's our lithotype, and you can see that basalt and schist are just kind of scattered throughout. They're not very common, and the schists are mostly along the boundaries. We got these 2 points that are contradicting, or 3 that are contradicting that. Then when I look at the outliers that are actually classified as outliers using the algorithm, I see these schist points here. I can see that, well, wow, the schist points are over representing the outliers, and I see this clump here. And so this leads authors to feel like we should get rid of basalt and schist observations from our data. Now, these points here, something's going on, something interesting is there. I know to dig into that, figure out what's going on. Hopefully it's not a mistake in measurements. It probably isn't. In this particular case, we would not exclude these on the basis of outlier analysis alone. By outlier analysis alone, yeah, I know it's there, but it's not like, pushing that hard. Now that I'm looking at it, I'm understanding that geographically things are much more complicated. And, these outlier points mostly overlap with the schist samples. And therefore, let's go ahead and exclude them. We don't have very many of them. And so I'll be like getting a more pure data set if I exclude these. So let's go ahead and exclude them. I like the keep drop convention for indicating keeping or dropping a row or a column. And so we use keep to say what I want to keep in my data. And so, if the lithotype is in the type I want to have, then, so what's happening is schist and basalt observations are being removed from the data set. We only have these two types of lithotype in our data. And so I'm going through, and all the objects I have in my analysis, I'm filtering out what I don't want. All right, we have covered a good amount of stuff. We talked about, wading, like the method of wading through our composition data, then our spatial data, then do the two of them together. We've talked about simple plotting of observations by coordinates on a map and coloring them. We talked about the swath plots, where I consider one coordinate at a time. Now, something that I could have done with that is also done like by principal component on our coordinate system. If I had like if the data was sampled like not parallel to north, south, east, west. And then we talked about like analyzing the examples that we have with us. Okay, so that's all I've got for you. Life is short. Do math.